Hey everyone. So I wanted to use a neural network or a machine learning technique to generate a depth image from a stereo pair. So basically I needed some training image. So I needed the stereo pair data and the depth image or the disparity image, and then I can use that for training. So I went to my usual place, which is Kaggle, and I had a look there for stereo images, but I couldn't really find that much. But I did find this one here, which is stereo images with ground truth, disparity and occlusion. So I thought I'd go and get those. And then when I went to the website, server not found. So now if you can't find the data, I guess you have to generate it yourself. So what I've got here, this is a stereo camera here, and then this is a time of flight camera. So I'm going to put these two together like that, and then I'm going to have I'm going to be able to collect the stereo pair and the disparity image all together, and then I'm going to back them onto this perf board just to keep them all aligned, because this has got like a grid structure on it, so I can keep all the lenses aligned perfectly when I do that, and record my own data, and then I can use that to train my neural network. So the next step now is to put everything together to mount these cameras onto the Raspberry Pi. So this is my stereo camera, which is this one here, and I'll link that in the description. You can get that from Amazon or the vendor of your choice. And then the Arducam I'm using is the time of flight Arducam camera, which has some instructions here, and I'll link these in the description as well. I'm using a 2mm drill bit to mount these, because this has 2mm holes in it, and everything's going to be connected to this Raspberry Pi here, which is a Pi 4, I think. Yeah, that's a Pi 4. So I'll put all this together, and then we'll bring up an image. I've mounted the stereo camera on the perf board, and then I put the Arducam Time of Flight camera on top of that. So I've got this kind of exactly in the middle of the two lenses, and I've counted the holes and everything to do that. And then I've got everything connected to this Raspberry Pi here, and I'm running Bookworm on the Raspberry Pi. You can also run Bullseye. I wouldn't recommend running anything less than Bullseye, anything older than Bullseye, just because you're going to get you might get some issues with OpenCV installation and that kind of stuff. I think OpenCV will install a little bit easier on Bullseye and Bookworm, in my experience, and other stuff. And now I've got the Raspberry Pi connected to my computer on this Tiger VNC. You can use a remote desktop or something. I'm running it in headless mode. I found the Tiger VNC worked the best with Ubuntu. So I'll make this a bit bigger anyway. So Arducam provides some code, some examples, and they also provide like a getting started guide for connecting this to the Raspberry Pi, for connecting the camera to the Raspberry Pi. And if you look at their code, they've got a demo sketch in the getting started guide, which is here. Maybe I'll make that a bit smaller so you can see that. So this is their demo sketch, but it's not going to work because some of these functions that they use in it, like this init, is deprecated. But on their GitHub, this stuff is, so this is the time of flight camera GitHub provided by Arducam, and this is updated fairly recently. Look, it's updated like 2-3 weeks ago. So this is all fairly up to date, and there's some examples in there, and there's also some instructions here about getting it configured. So I'd read the GitHub in conjunction with these instructions here when you're going to install it on the Raspberry Pi. Okay, the other thing I should mention is that you have to have, if you're using Bookworm, you don't have to do this with Bullseye, but if you're using Bookworm, you need to have it running in a virtual environment, because you can't install the Arducam libraries unless you're using a virtual environment. So I think that's just a feature of Bookworm. Okay, let's go to Thonny now, and I'll show you the code I've written just to get it as a demo. So this code will open both the 3D camera, which is the stereo camera, and the time of flight camera images. So we'll have a look at that. Let's make sure we're in our virtual environment first. Okay, so you can go to the interpreter here on Thonny and set it to your virtual environment. So now let's run that and hopefully we'll be able to pull up some images. Let's just organize these. Okay, so this one here, this top one, that's the stereo camera. And then this bottom one here is the distance from the time of flight camera. So if it's white, it's really close. And as it goes more grey, darker, it's further away. And then there's also another one behind this, which disappeared behind there. So the time of flight camera outputs 2 images. And this one here with preview, this grey one, this gives you the distance. So this is the timing. This is how long the photon takes to return to the sensor. And then the bottom one is the intensity of the photon. Alright, so now I've got this working. I can go and take some photos and I can collect like a database of stereo pairs and disparity images that are like calibrated, and I can use those for training machine learning techniques or whatever other technique I need to train or calibrate. Hey everyone, so I've mounted the cameras in the Raspberry Pi on top of this piece of Perspex here, and I've connected this battery here to it just so I can make it portable and I can just take it anywhere I want. And I'm also using this USB hub which has its own power supply basically, just so I don't draw too much power from the Raspberry Pi. And then I've got it up on the table here and I'm just going to photograph. I guess you can see I've got a bit of a theme going. I'm just going to photograph some cups and then I might get some cereal boxes later as well. I've recorded a few short videos with a 3D camera and I'll just show you those now. So this top one is from the time of flight camera and this is the ground truth disparity, and then this is from the stereo camera, and we see the Sultana brown box is a bit kind of a darker grey and the Weet-Bix box is brighter. That's because the Weet-Bix box is closer to us. So basically if it's brighter it's closer to us, and if it's greyer it's further from us. If it's darker it's further from us. So the reason I've done these videos, I recorded these videos instead of, I guess, taking photos, is because like from a video I can get a lot of frames. So I just extract the frames individually from the video and then I get like 20 photos at once rather than having to take 20 individual photos. And as I take the video, I'm moving the camera around, and this is kind of, so each frame is going to be a different photo. And this is, I guess, like doing augmentation on the data. So I've used this now to train a convolutional neural network. So to train, this is the input, the stereo pair is the input, and the disparity, the ground truth disparity image from the time of flight camera is the labeled data. And I'll show you how I've done that. I've done that in a Python notebook. But first I'm just going to show you quickly the code I used to capture these images, to capture the time of flight and the stereo camera image. Just show you a couple of things from that. So I'll just make that a bit bigger. Alright, so let's go down to the main function. So here I do a record. So when I press the R button, I record from the stereo camera and the time of flight camera, and I record for 3 seconds, I think. So here it is. So if I press the R button, I record for, I wait 2 seconds and then I record for another 2 seconds. So I wait 2 seconds to give me time to move the camera, and then I record for another 2 seconds after that. So each recording goes for 2 seconds, and it's, I'm not sure, it's probably about 10 frames per second. What else did I want to show you? Okay, so we're getting 3 frames. We're getting the frame from the stereo camera, which is this one. We're getting the 2 frames from the time of flight camera, which is the depth buffer and the amplitude buffer. So we use the amplitude buffer is the intensity of the photons. And what we do, this process frame, what it does is it thresholds the depth frame. So if the amplitude if the intensity of the photon is less than a certain value, we threshold that to 0 because we ignore that because if the intensity is too low, it means we can't get a very good reading. And I spoke about that a little bit in my other video, which I'll link in the description. But for now, I'll show you how I encode, how I train the data. So the convolutional neural network, where I use these as the input training data, and this is the label data. So I'm using a convolutional neural network, and the structure I'm using is called an autodecoder. So it has an encoder and a decoder. So first we have our input here, and then basically we do a convolution on this and we downsample at each layer. So now what the convolutional neural network does is it preserves, I guess, the structure of an image, and there's loads of videos on this on YouTube, so I'm not going to repeat any of that here because I'm definitely not as good as explaining it as some of these other guys are. Like, my recommendation would be someone like Andre Karpathy. But so what this does is, so at each point we downsample this, and then this is the encoder, and then this is the decoder. And so our output here is an image, and then our input here is also an image. So that's our input. And the thing is, I guess, like I said, the convolutional filter preserves the structure of the image. But so this here, this thickness is one for each convolutional filter. And what we do is we kind of stack them on top of each other. So we get lots of layers. And so, so my input is basically my stereo image, and my output, which I've trained here, is going to be my ground truth disparity images. So basically, in my case, I've got my two stereo images, one here and one here, and then I've got all my convolutional filters. These are W1, W2 to W9, and then a whole bunch of these. So these weights here, these are randomized at initialization, and then these are determined through training. So we don't actually have to determine what kind of convolutional filter we're going to use. So basically this goes through this, and then outputs here, and we downsample as well. So we run the CNN with downsampling, which we use what's called max pooling, and then we do the same for this image. So this is the left image and this is the right image, and then we have this, and then we concatenate these two. So we do this, we put them together, and then we upsample, do another convolutional network, and then upsample, and then another upsample, and that's our output. And we try and force this output here to be the same as our disparity image. So we kind of, we use like a function that we minimize, and when that function is minimized, this will be the same as our disparity image. And we change the weights so that we minimize this function here. So I'll show you that now in the Python workbook. This is the notebook that I'm using for the convolutional neural network for disparity image generation from stereo pairs. And so the input is basically a stereo pair and the output is a disparity image. And I'm using the ground truth time of flight disparity images to train it. And I got this idea from this tutorial here, which this guy here, he's using a CNN-based autoencoder to denoise some handwritten digits. So this is his input here, which is a very noisy handwritten digit, and this is his output, and this is a network he uses. and I'm using like two images as an input, so a left and a right, and then I use a concatenation like round about close to the middle, and then my output is the disparity image. So I've kind of followed this, but I've changed up some of the parameters, and he explains all that. I'll link that in the description. So I'll show you the notebook now. So basically the first thing I do is I bring in all my objects and functions from Keras and TensorFlow, and I'm using Python 3.10.12, and then this function here which loads the images from directories. So input directory has the left images 1, input directory 2 has the right images, and output directory has the time of flight disparity images. And what I do when I load the time of flight disparity images is I take a median filter, and the median filter is just basically to clean up some of the noise. And a median filter is really good for cleaning up impulse noise. So it's a low pass filter, and it cleans up impulse noise and preserves the edge structure in the images. So I'll just show you that quickly. So this here is the image without the median filter. I'll just make myself a bit smaller so you can see a bit better. So the one on the left is without the median filter, and the one on the right is the filtered image, and we see that this has cleaned up a lot of the noise. Alright, and also, okay, the other thing I should say is this extract frames notebook I've used to extract the frames from the video, and I'll put that on my GitHub as well. Alright, so now we've loaded the images, we have to shuffle them. So we shuffle the order, but we have to preserve the order, so we have to do the same left, right, and disparity image, and then we take the first 20 images for training, the first 20 images for testing, and then from 20 images onwards we take for training. So the first 20 images I don't use at all in the training, and then I only use them for my testing afterwards. Now we create the network, and this is created with Keras. So the input is just the two images, 180 by 240, and I've kind of trimmed the stereo images down a bit because the stereo image has a wider angle. The camera has a wider lens angle than the time of flight camera, so I've cut off the sides and the top and the bottom a little bit for this. So I've made everything 180 by 240, all the images. And so this is my network which I build, and then I guess the best place to show you is in the network summary. So this is the summary here. So it firstly has an input layer, which these are the two images, and then we do a convolution on each of these images, and then we do max pooling, which is downsampling, and then we concatenate. So we put the two images basically into one. We stack the outputs on top of each other in a sense, and then we do like 4 convolution filters, and then we do max pooling again, and then another convolutions filter, and then we upsample and do another convolution filter, and then upsample again and do another convolution filter, and our last convolution filter outputs are 180 by 240, and that's what we compare with our disparity image, our ground truth, which is like our label data, and we try and adjust the weights so that we make this output image that will equal our ground truth data. So this is just how I've structured it now. You can basically change the structure around and experiment with different weights, and like I said, this is only just to demonstrate what we can do with this data. It's not actually like where it's going to end up. It's just for demonstrative purposes. Okay, now we can compile our model, and we can either use binary cross entropy, because we're using a sigmoid activation function in the output layer, and all our values are between 0 and 1. basically we've scaled our grey levels. We've divided by 255 so that everything's between 0 and 1. We can use binary cross entropy loss for our regression, and it works with regression as well because just because of the way the formula works. The other loss we can use, if we don't want to use that, we can use mean square error. All right, and now we do our training. So we train our network. So this next cell here is model fit, and I'm using a batch size here of 32, and this batch size you might have to adjust that if you run out of memory. You're going to have to lower that, and 500 epoches. I'm not actually going to run this because it's going to crash the computer, because I've got OBS running as well, and OBS is going to be using up a fair bit of memory. So here's what I prepared earlier, and I'm just going to load that, and then we can see how that works. So now we run predict on our images, our test images, which were our first 20 images. And then we have a look at, so basically we've normalized everything by dividing by 255, and then we multiply again by 255 just to get the grey levels. And then we just look at our shape. And now let's just plot them all and see what our 20 images are like. All right, so so this is our stereo pair. So this is our left image, our right image, and this one here is our original image. That's our ground truth image, and this one here on the right is the output of our network. And I mean, these look pretty good. I mean, this is just a rough and dirty implementation. I haven't used any skip connections. I haven't used any dropout or regularization or batch normalization or any tricks or any fine tuning. So this actually looks pretty good. I mean, we see the Sultana brand box, which is closer here, and in the output from the network, it's closer here. See this image here, the ground truth image for this particular sample hasn't actually been used. So it's just, this has just been output here, and that's what the ground truth looks like. And then the matzo box is like pretty close to us, and we see the chair here, and this kind of looks almost the same. The wheat picks box, very good. So we can do some post-processing afterwards, and I don't even know if these results are so good because it's overfitted. So that's something I'd have to investigate, but this is definitely looking promising. And I'll put all this up on GitHub, and you can have a look at it, and hopefully I'll see you in the next video. Thank you for watching.